Section 5.8 is all about quadratic applications and their use in the real world and how they can be applied to different situations. One of the most popular situations, if you want to call them purpose or uses, one of the most popular things is objects that fly through the air. Because if you throw a ball, for instance, the ball goes up and then back down, which forms a parabola. Any objects that fly through the air will make a graph described by a parabola. Second, such things as in business or applications, when you're dealing with setting prices versus how much profit you make. And this example I'll actually describe for you in class. But prices versus profit is another example of where quadratic functions can describe a problem. 3, areas, lengths, and widths, especially when it comes to maximizing that particular information. If you want a maximum length or a maximum width if you're building something, areas are another good application of where this is used, because area is a squared concept. So as you see, and as we go through some of the examples in class, you're going to see that there are a lot of uses for quadratic applications. Now, let's do one together. I'm going to forward the slide. And I have a very nice picture that I drew here of John. John's punting a football that has an initial upward velocity of 80 feet per second from a height of 2 feet. And obviously, the path of the ball is going to make this nice parabola. It's going to go up, and then it's going to come back down, and it's going to strike the ground somewhere over there. Now, first and foremost, we need an equation. We need a quadratic equation that's going to summarize the height of the ball over the amount of seconds that it's in flight. Well, our two variables are going to be time and the height of the ball, because as time goes along in this direction, your heights are going to go up and then it's going to come back down, which is where our parabola or our quadratic equation comes from. So, to write a quadratic equation, when you're dealing with objects in flight, and I'm going to write this down for you, objects in flight, your equation is in 3 parts. We know the function is ax squared plus bx plus c. Well, when you're dealing with objects in flight, the a value is gravity, and that's always going to be negative 16 if you're talking feet per second. The b value is its upward velocity, and the c value is where it starts. So if I'm going to write my function, the height of my function, h, is equal to, and gravity pulls the ball down, so that's negative 16x squared. That's always gravity. I'll underline that. Plus, since it's going upward initially, the upward velocity is 80 feet per second, so that'll be 80x. And then the last number is where it starts. So I'll underline the 80x, that's its velocity. And then where it starts, it says it starts from a height of 2 feet. So that's plus 2. And that will be the equation that we are going to use throughout this particular problem. So if you need to pause the video, please do, and then I'm going to go on and we're going to answer some questions about this situation. I redrew my picture of John, and I'm going to rewrite my equation. The height is given by negative 16t squared plus 80t plus 2. So, first thing we need to talk about, we want to know what's the maximum height of the ball. Well, if you look at my picture, which I'm going to put up here in red, here is the maximum height. Well, we all know that that point is called the vertex. And from all the prior things that we have done about vertex, that's what we need to find. Well, the vertex, the x-coordinate, and I'm actually going to draw an x and y-axis on my picture here. Here's the y-axis, and here's my x-axis. Obviously, the x-coordinate of the vertex is the line of symmetry. So we know that the vertex, the x-coordinate, the line of symmetry is negative b over 2a. Well, b is 80. So I'm going to put negative 80 in there, all over 2 times a, which is negative 16. Okay? So my vertex is going to come out to be negative 80 divided by negative 32, which actually comes out to be a time of 2.5 seconds. So actually, that's the answer to question 3. If you look here, it says, what time does it take to get to its maximum height? Well, that answer is 2.5 seconds. That's the x value. But the question says, I want to know what its maximum height is. I want to know how tall that is. What's the highest it gets to? So basically what we need to do now is we need to take 2.5 and plug it into our function. And if you take your calculator and you go ahead and you type that in to your quadratic function, you would soon find out that you get an answer of 102 feet. So when I plug that in, what's the maximum height of the ball? The ball will get to 102 feet in the air. That is the y value. So h, I'm going to write in here, is 102. So I hope that helps you understand how to find maximums. Anytime it asks you for maximums or minimums, if it asks you that, to find those, use the vertex. Very important note to write to yourself. Number 4, what is the y-intercept? Well, if you remember the y-intercept, to find the y-intercept, you put 0 in for x, or in this case, it's t. Well, if I put 0 in for t, and we've already talked about this, the c value is my y-intercept. The c value is 2. Now, what does it tell you about this problem? Let's say right here is 2. Well, what it tells you is that is how high, that is how high the ball is when John kicked it. It was 2 feet off the ground. Obviously, he's going to kick it about right there. The ball's got to be off the ground when you punt. So that's what the y-intercept tells you. And now the last question, and maybe the most important question. I'm going to go back to the picture. I want to know what time this is when the ball finally strikes the ground. How long is the ball actually in the air? Well, I'm going to draw a picture again. When the ball finally hits the ground, what is true about that point? Well, what is true is that the height is equal to 0. So in our problem, we had a function of negative 16t squared plus 80t plus 2. And what I need to do is I need to plug 0 into that function for h, because I want to know what time it is when the ball hits the ground. Well, basically, that's solving a quadratic equation. From what you've learned throughout this entire unit, in order to solve a quadratic function, it has to equal 0. Well, this is not going to be factorable, so I believe we need to use the quadratic formula to come up with our answers. So, if you remember the quadratic formula, x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So I'm going to plug all these numbers in. Here's a, here's b, and here's c. So my answer to the problem when the ball finally hits the ground is going to be negative 80 plus or minus the square root of 80 squared minus 4 times negative 16 times 2. That entire thing divided by 2 times negative 16. Well, as we've discussed before, figure out the value of the discriminant first. Do this first. Okay? And I believe you come up with an answer of 6,528. So I get negative 80 plus or minus the square root of 6,000. Oops. Got to go back a second. Negative 80 plus or minus the square root of 6,528 all over 2 times negative 16, which is negative 32. Now I'm going to estimate that square root. If you come up with the square root of 6,528, you get an answer of about 80.79. So I'm going to write my two answers. My two answers to this problem are negative 80 plus 80.79, the whole thing divided by negative 32. Or the other answer when the ball hits the ground is negative 80 minus 80.79 divided by negative 32. Now I'm going to do a little bit of erasing here so I have a little bit of room. If you actually type these in your calculator, put these in parentheses, if you're going to type the whole thing in, this answer comes out to be negative 0.02 seconds. And this answer comes out to be 5.024 seconds. Now, which one makes sense? I'm going to go back a slide to my picture. If you remember, he kicked the ball starting in the air. Now, if I would continue this parabola down, here is negative 0.02 seconds. That's one time when the problem equals 0, but that doesn't make sense. The only answer that makes sense is 5.02 seconds, and that is this point of time right there. So I'm going to go back. So the answer to my question, when will the ball finally hit the ground, is 5.02 seconds. And I hope that explains some of the most important points and features of a graph that is a parabola and how it's used to answer a real-life problem. If you have further questions, please ask me in class.